Good afternoon. So to finish up Friday, which is today, Friday, we're going to be working on section 2.6. And though it's going to be a whirlwind, we're going to start and finish 2.6 altogether. So feel free to take the weekend to look over this content. Homework 2 does not have anything to do with this. So feel free to work on homework 2, maybe rewatch this video. It's going to be a long one, but that's okay. So chapter 2, section 6 is all about continuity. And continuity is a different idea, but very similar to the idea of limits. And this is what we've been working towards for the past couple of days. So we're going to start with continuity at a point. Just like we took limits at a point, we're working at continuity at a point. And we say that a function f is continuous at a if the limit as x approaches a of the function f of x is equal to f of a. Now, we saw previously that f of a need not even exist for the limit to exist. But in order for it to be continuous, the limit needs to exist, the function needs to exist, and they need to be the same value. So that brings us to the next slide, which is continuity at a point, the checklist. So first of all, to check that some place is continuous, that a point is continuous, f of a has to be defined. So we can't have any open circles. We have to either have filled in bubbles, or we've got to have a line going through a point. Second, we need the limit at x as x approaches a of f of x to exist. It doesn't matter what it is, it just has to exist. And then third, it does matter what the limit is. The limit has to exist and it has to equal our function at a. So if one item on our checklist fails, then f is considered discontinuous at a. So anytime we have an open circle and then a bubbled in point somewhere else is considered a discontinuity. Anytime we have an open bubble but nothing defined anywhere, we've got a discontinuity. So let's use this example, and I'm switching up how I'm doing examples just because I want you guys to get a little bit more out of them. So here, and let me know afterwards, send me an email or I'll make a poll or something like that, and you can tell me if it's any better. So in this example, I want you guys to use the graph of f to identify the values of x on the interval 0 to 7, at which f has a discontinuity. And remember that a point is discontinuous if it is not continuous. So go ahead, take a moment and pause this video and look and find all the places from 0 to 7 on this graph where f is considered to be discontinuous. So take a pause and come back in a moment. So hopefully you paused and now you're back because this is the answer slide. So f is going to be discontinuous at 0, where we've got an open bubble and no black dot. At 1, again, we've got an open bubble and no black dot. At 2, we've got an open bubble, but the black dot is somewhere else. So our limits exist from the right and left, but they don't equal f of a. At 3, we have the exact same problem. Our limits don't equal each other, and neither of them equal f of a, which means the limits do not exist. And then again, we have this problem at 7. Now, is there anything I'm missing? What do we think goes on at number 5? And I won't answer that for you. Next, we're going to talk about continuity rules. So just how we have limit rules, like the limit of f plus g is the same as limit of f plus the limit of g, we have the same sort of rules for continuity. So if we've got a function f and a function g, and they're both continuous at a point a, then the following functions are also continuous at that point a. And in this case, we're going to let c be just some constant. Maybe it's 7, maybe it's 13. It doesn't really matter. And we let n be some non-negative integer. So f plus g will be continuous, f minus g, c times f, so your entire function times a constant, the product f times g, f divided by g, provided that g at the point a is not equal to 0, and a function f of x raised to a power n, where n is just a non-negative number. If any of the base functions are continuous, then these derived functions, these functions that come from something else, are also continuous. So that was Theorem 2.9. Here is Theorem 2.10. Theorem 2.10 is all about polynomials and rational functions. And we say that a polynomial is continuous for all values of x. And if you use a graphing tool like Wolfram Alpha or a graphing calculator and you just type in some polynomial function, any polynomial you want, you'll see that you can draw a line without picking up your pencil. There's no open bubbles. There's no open bubbles and black dots. It's just a continuous line. Rational functions, that is a polynomial p divided by a polynomial q, are continuous for all x when q of x does not equal 0. So in this case, we might get a few places where our function is not continuous, but we're going to get the majority of our lines as continuous. So again, another example, and we're doing it in this new example type. So the question, for what values of x is the following function continuous? And this function is x divided by x squared minus 7x plus 12. So go ahead and hit pause and see if you can't work this out and come back and we'll have an explanation. So here's the explanation. Because f is a rational function, the previous theorem that we just saw, theorem 2.10, tells us that f will be continuous for all values of x where our denominator, x squared plus minus 7x plus 12, does not equal 0. So we can go ahead and factor our denominator into x minus 3 times x minus 4, which means that we're going to have zeros at positive 3 and positive 4. This means that f will be continuous for all values of x that we want to choose except at x equals 3 and x equals 4. So now let's talk about composite functions. We saw a lot of different ways to combine functions in the previous slides, but this is a different way to combine functions. So given two functions, f and g, the composite function fg is defined by fg of x, which is the same as f of g of x. So in this case, we take a value x and we plug it into our black box, our function called g, and we get some sort of output. That output we then put into our function f, and we hope to get a viable output from there. So if we talk about composite functions and we're on a chapter in continuity, then we're really interested in the continuity of composite functions at a point. So if g is continuous at a and f, our outer function, is continuous at g of a, then the composite function fg is continuous at a. And this kind of makes sense, right? If there's a discontinuity at a, then g isn't continuous, so nothing we put inside of f can make it continuous. But if g is continuous at a, then we've got a pretty good chance of ending up with f being continuous there too. And here's a formal theorem about that result. So if g, our inner function, is continuous at a point a, and f, our outer function, is continuous at g of a, then we can write the limit as x approaches a of f of g of x is the same as our function f of the limit as x approaches a of g of x. And what exactly does this look like? Well, this looks like something that we'll see in an example or two. So example 1 is evaluate the following limit. And this is the limit as x approaches -1 of the function square root of 2 times x squared minus 1. And the thing you want to be careful about is what are you choosing to be your outermost function and what are you choosing to be your innermost function? So take a pause, maybe get some water, work on this question, see how far you get, and then come back and see the answer slide. All right, here's the answer slide. So we're going to let our inner function be 2x squared minus 1. So everything that's within our radical. We know that it's continuous and positive at x equals -1. I'll have to redo this side because I said it's continuous and positive is continuous and positive. It's continuous and positive at x equals -1, and 2 times -1 squared minus 1 is equal to 1. Because our radical is continuous at 1, we can write the following. Limit as x approaches -1 of the square root of 2x squared minus 1 is the same as the square root of the limit as x approaches -1 of 2x squared minus 1. Well, we already showed that our inside function limit is just plugging it in. It's just 1. So the square root of 1 is 1. And that's how we find the limit of our big function. So we've talked about continuity on a point, and it's tempting to ask, well, what's the continuity of a whole line or a part of a line? And that's called continuity on an interval. A function f is considered continuous on an interval I if it is continuous at all points of I. If I contains its endpoints, the function must be continuous from the right or left at the endpoints. And I've got a few diagrams to help show us what this means. So here I've got a diagram drawn on the left-hand side of your screen, and I've got two open circles at A and B. And I'm saying that my function is continuous on the open interval from A to B. And in this case, where our interval does not contain endpoints, our function needs to be continuous only between a and b. We don't really care what happens at a, and we don't really care what happens at b. Here, I've bubbled in the point at a, so we're continuous at a, and now I'm saying continuous on inclusive a, exclusive b. So this is the case where our interval contains only the left endpoint, and our function needs to be continuous between a and b, certainly, but it also needs to be continuous as a right-hand limit at a. So there's nothing for us to do from the left, there's only stuff for us to do from the right, so that's what we care about. Next, I've just got the opposite. So I've got A open and B bubbled in, and this is the case where our interval contains the right endpoint, so our function needs to only be continuous between A and B, and then be continuous from the left at B. Now you're saying, well, if I can do it from the right endpoint and the left endpoint, I better be able to do it for everything. So this is going to be continuous from A to B, including our endpoints. So including both of our endpoints, our function must be continuous between A and B, and at A from the right, and at B from the left. So that's a lot going on, but let's see some homework questions about that. We're 20 out of 28 slides deep, so I promise, I know it's maybe easier to receive this sort of stuff in class, but hopefully with YouTube, you can pause, take a break, really get your mind right and be in the mood for this sort of stuff. And it's not going to be taken down anytime soon. So now that we've looked at continuity at endpoints, we're interested in continuity of functions with roots. So let n be some positive integer. So in this case, n could be 2, maybe it could be 17, maybe it could be 3. If n is odd, then the 1 over n power of f of x is continuous at all points at which f is continuous. If n is even, then the nth root of f of x is continuous at all points a at which f is continuous, and f evaluated at a has to be greater than 0. Now, you're probably wondering, well, why is it different for even and odd roots? And it just has to do with when we end up with imaginary numbers and when we don't end up with imaginary numbers. We have to make sure that if we've got a square root or a fourth root or a sixth root, that we don't have any negative signs on the inside. Otherwise, we're in the realm of imaginary numbers and we don't know how to deal with that. So let's look at some examples. Question 1, for what value of x is g of x equals square root of 9 minus x squared continuous? Just like all the others, go ahead and take a pause, work on this as best you can, and then come back for the answer. So here's our answer. On the left, I have drawn the graph of g equals square root of 9 minus x squared, and it looks like just a half circle that goes from positive 3 over to negative 3. So the graph of g is the upper half of a circle, x squared plus y squared equals 9. And it looks like g is continuous from negative 3 to 3, including both of our endpoints. So obviously we've got a straight line, and if we plug in any of the values on the inside between negative 3 and 3, we're going to get a positive number, so our square root is going to be valid. So we need to only check the endpoints. So if we check negative 3 from the right and 3 from the left, this shows us that these endpoints are continuous because they both equal 0. We can take the square root of 0. That's totally fine. So the limit as x approaches negative 3 or positive 3 of g of x equals 0, and both of those equal 0. That's exactly what we want. So checking shows us that this is true, so g is continuous from negative 3 to positive 3, including our endpoints. And I think we've got one more example here. Yes. So for what value of x is f of x equal to x squared minus 2x plus 4 to the power 2 divided by 3 continuous? So this might seem a little bit daunting, but go ahead and give it a try and come back to see the answer slide. So here's our answer. We know that x squared minus 2x plus 4 is continuous for all values of x because it's a polynomial. We have that in a theorem previously in the PowerPoint. We can rewrite f of x as x squared minus 2x plus 4 to the power 2, and all of that to the power 1/3 because of our power rules that we learned back in algebra. The result of squaring whatever value we get out of our polynomial will always be positive, and we know that f contains an odd root. Because f will always be positive and continuous, f is continuous for all x. So we've done algebraic functions, we've done rational functions, we've done polynomials. Now it's time to get to these nasty transcendental functions. And I'm going to break this up into a couple of slides. Really, the only thing I want you to know is just copy these down. Remember that they're continuous for all the points in their domains. So first of all, we've got trigonometric functions. So sine, cosine, tangent, cotangent, secant, and cosecant. All of these functions are continuous at all points in their domains, no matter what. We've also got the inverse trigonometric functions. So sine inverse, cosine inverse, tangent inverse, cotangent inverse, secant inverse, and cosecant inverse. All of these are, again, continuous at all points in their domains. So whatever is a valid input for these functions, they're going to be continuous. Next, we've got the exponential and logarithmic functions. And you might be saying, Emily, what are all these numbers and what are all these letters? But it's okay, we're going to work through it. So I say that the function b to the power of x is continuous at all points in the domain. And what I mean by b is that it's just a number. We could pick -1, we could pick 16, we could pick whatever your favorite number is. And when we raise it to a power x, it's going to be continuous for all points x. Now, e to the x is very special. It's going to be continuous for all points in its domain. And then we've got log base b, where b is just some number. Typically, if you don't see a base b, that means base 10. But log b of x is going to be continuous at all points in its domain. And then finally, the natural log of x is going to be continuous for all points in its domain. And we say all points in its domain because we know that for e of x, we can put in anything we want. We can put in negative numbers, we can put in positive numbers, we can put in fractions, we can put in radicals. Anything we put in there, it's going to be fine. But when it comes to the natural log of x, we can only put in values between 0 and positive infinity. We can't ever put in a negative value, we just get an error. You can go ahead and try this on your calculator, and your calculator is just going to get mad at you. So finally, we come to probably the most important slide in this entire PowerPoint. So if you were just breezing through all the others, just writing them down, not really thinking about it, I want you to pause, read through this, go along with it with me, and then consider writing it down. So this is the intermediate value theorem. And again, if a theorem has a specific name instead of just theorem 3.5 or theorem 2.1, then it's really important. So this one is really important. If you take nothing else away from this PowerPoint presentation, then this is what I want you to remember. So suppose that you've got a function f and it's continuous on the closed interval a to b. So we're including the endpoints. And L is some number strictly in between f of a and f of b. Then this theorem says that there exists at least one number, c, in between a and b, such that f of c equals L. If you look to the left-hand drawing, you see I've drawn sort of just a curve and it's got two endpoints, one endpoint at a and one endpoint at b. And if I just pick some value L in between f of a and f of b, I can always march my finger across and hit some point on that line. And when I drop down, there's going to be a value between a and b. Now, the theorem guarantees that we've got at least one number c. But if we've got a function like cosine or sine that oscillate, then maybe there might be more. So if you look to my very crude right-hand drawing of some oscillating function, you'll see that I've picked an L in between which our function passes through it 4 separate times. So in this case, we're guaranteed not only one, but 4 instances at which our function passes through this line. And that's very, very powerful. And we're going to use the results of this theorem a lot later in this course, but it's very, very important. So take a moment, take a deep breath. Maybe now it's time to write down what I have written, and you'll see some homework problems posted, and you'll be able to work with this a little bit. All right, that's it for me.